quickly whip through what they are. Any mistakes that I make are entirely my fault rather than the work of the scientists, and similarly my pronunciation of people's names, the disaster, it will be my own fault. So the first talk is poster 307, which is about variability of classical T-Tauri stars by Yukako Aimi, who uses tri-spec on the Titani telescope on Hiroshima to study simultaneous variability in the optical and the near-infrared of 27 YSOs. They find that the sources all show significant variability, and they want to ask what is the cause of this variability. When they have a look at the colour magnitude relation, it suggests that while star spots are certainly the cause, it's not the only cause. So if you want to have a look at what some of the other causes are, go and see poster 307. Poster 308 is by Mary Barsoni, who presents a novel method of identifying pre-main sequence populations in star-forming regions, irrespective of the presence of whether they have disks, and this method can distinguish between members of the cluster and background sources. They test the method on IC348 cluster, and they recover all of the spectroscopically identified members of that cluster, and then they apply the technique to row off. They find 1,000 new brown dwarfs and pre-main sequence candidates, and 80% of those have near-infrared excess indicative of disks. So you can go and have a look at those nice new results. Poster 309 is by William Best, who has a look at the gas content of protoplanetary disks. They use a model that shows that the optically thin CO isotopolog emissions scale with the mass of the gas, and that this has the potential to constrain the gas mass to within a factor of 3, which basically means that their method does a lot better than using the completely unrealistic canonical gas to dust ratio of 100, so that's great news for everybody. Poster 311 is by Christian Clanton, who studies how binarity affects the location of the ice line, and they... well, this one, because I can't get the talk on that other one. Yeah, but it doesn't work. He has a look at the binarity to see how that affects where the ice line is, and basically what he does is he compares the location of the ice line with the critical radius within the circumbinary disk. Means that inside of that critical radius the orbits of planets would be unstable, and what he finds is that the ice line is basically inside of this critical radius for about 30% of the binaries that have a total mass of less than 3 solar masses, and this is going to have a problem for forming rocky planets because they need to form inside the ice line. Okay. Hit the red button. Thank you. Does anyone else wants to come up and give my talk for me? That'd be lovely. We'll see how we're going now. Oh, it's beautiful, except we're back at the start. That's okay. Okay, right. So, did everyone get to see those slides while I whip past them? There they all are. Number 8, number 9, number 11. Right, so poster 312 is by Maria Dewan Olivar, who investigates the discrepancy between submillimeter and near-infrared photometric images in debris disk structure. So basically that the submillimeter, you have submillimeter gaps, but these seem to be filled in by small grains in the near-infrared. So they run some simulations of planet disk systems with a 2D hydro and dust evolution code for different planet masses. Then they run a radiative transfer code MC max to make scattered and emission images for 3 different instruments. So if your favourite instrument is Sphere or High-Chow or ALMA, you can go and have a look at these, and basically they find that the radial distribution of the dust depends on the planet mass, that the submillimeter is tracing those large grains that are trapped at some pressure bumps, and while the little grains are moving in. And if you do multi-wavelength observations, then you can help constrain what the planet mass is. Poster 313 is by Julien Foer, who studies the inner boundary between the MRI active and inactive regions in the disk, so the inner boundary of the dead zone, and basically they find that there's a complex interplay between the turbulence and thermodynamics, because you have this turbulent heating as well as thermal ionisation, and this kind of creates a sort of feedback loop, and basically the edges of the dead zones are actually quite dynamic regions where waves and travelling fronts can affect things. So go and have a look at that poster as well. Poster 314 is by Kate Follett, who uses MAG-AO to present the first ground-based adaptive optics images of an Orion disk in silhouette. what they do is they use SED modelling for the radial brightness profile and the radial extinction profile of the source, and that allows them to peer further into these sources than HST has, and what they find is that the inner 2 AU is cleared. They also have a very nice description of MAG-AO if you want to learn more about that, and Kate very graciously reminds us all to keep calm and close the loop, which is always good advice. Then poster 315 is by Antonio Hales. They use APEC and ASTI to map the dust continuum and the gas emission in a submillimetre in bright Herbig star DX char. They find this double-peaked CO, which is typical of a rotating disk. They then use a radiative transfer code MC-FOSS to model the SED. They can reproduce the CO line profile and can constrain the disk geometry. They also present some simulated ALMA observations, which I assume is for all the ALMA TAC to give them time, so this is going to be a great source to look at. And poster 316 is by Mark Jews, who is studying the formation of protostellar disks. And there's a problem in that hydro simulations can easily make disks through conservation of angular momentum, while when you add magnetic fields, the fields will lead to strong magnetic braking, and this can prevent disks from forming. So what they find is that if there's a misalignment between the magnetic and the rotational axes, even by just 20%, then this reduces the magnetic braking because you get this shorter lever arm, and so massive disks can form. They also find that turbulence has two effects, which is that the random velocity field induced by the turbulence can tilt the rotational axes, which then helps produce these big disks, and also the turbulent diffusion also reduces the magnetic braking. So both of these things help form the disks. Okay. Go and have a look at that poster. Poster 317 is by Marinus, who studies the disk fraction in two young deeply embedded clusters. They investigate the dependence of the disk fraction with the stellar mass, looking just in M and K stars, and in a cluster environment. And what they find is that in one cluster, the disk fraction decreases with the stellar mass from M to Ks, while in the other more sparsely populated torus-like cluster, the reverse trend is found, and that the disk fraction is increasing with the stellar mass. So whichever the case is, they're finding that the stellar mass is certainly dependent on the evolution. So you can have a look at that poster. And poster 318 is by Rebecca Martin. They are looking at the evolution of the snow line in protoplanetary disks, and they have two models. The first one is a steady state full turbulent disk, and the other is a time dependent disk with a dead zone in it. And what they find is that the fully turbulent disks, the ice line is inside of 1 AU, which is going to cause a problem in our system since we have quite a water poor Earth. While when they have dead zones, this prevents mass transfer, and so the outer part of the disk becomes gravitationally self-gravitating, and then that increases the temperature, and so the snow line moves out. Poster 319 is by Eloise Mayo, and she's simulating large-scale Rossby vortices in 3D in disks rather than previous Rossby wave vortices, which are 2D simulations. And what she finds is that the 2D models match all of the 3D models match all of the 2D results, but also when you add that extra dimension, you always get some more information, and these new 3D simulations show vertical size sorting of the dust in the vortices, so that helps planetesimals form. And once they've got really quite large grains, then you get this back reaction from the gas on the dust, and that also helps things along. Poster 320 is by Fazana Meru, who has a new physically motivated method to study dust coagulation and fragmentation. They've suggested that it's been suggested that, I don't actually know why this is suggested, so maybe someone can tell me, that we don't expect grain growth in brown dwarf disks, but anyway, grain growth is observed to millimetre and centimetre sizes. So the question here is it true that brown dwarfs are just scaled down T-Tauri disks? And if that's the case, then how would grain growth proceed? And what they do is they try it and they find that basically it's the same thing, and they do get grain growth. So that's great news. Poster 320 is by Henry Ngo, who studies giant planet core formation using the new LiPad integrator, which are basically an extended version of SIMBA. The simulations include planetesimal growth via collisions and also decay of the gas disk between 1.5 and 3 million years. And what they find is that planetesimals can grow from 5 kilometres up to cores, protoplanet cores with masses of 3 to 5 Earth masses within about 4.5 million years, which is pretty good because it's not too far off the 10 Earth mass sort of critical mass to collect the envelope. And then poster 322 is by Chris Ommel, who has a look at inviscid and viscous flows around embedded protoplanets. And they're having a look at the average densities and velocities pattern flows, and they're basically zooming in on the atmosphere, and they find that the flows can be asymmetric due to pressure support, and they include some tracer particles, and they have some nice simulations, so go and look at those. Poster 324 is by Jake Simon, who their goal is to characterise the strength and structure of MRI turbulent disks. They do 3D simulations in local patches within the disk. They find that the strength of the turbulence, which drives the mass accretion, strongly depends on the vertical magnetic field that threads the disc. He also has a link to our website, which has some beautiful movies. So you can go and stand there with your iPhone and look at these great movies. That's quite fun. My last two, great. And poster 326 is by Matthijs van der Wiel, who has some spire observations of 5 Herbig stars. And what they do with spire is it gives you 10 CO lines simultaneously, and that can help provide information on the temperature of each disk. And when I asked him, what does he want me to say, he said, basically I want people to come and tell me how to interpret the data. So go and help him out there. And you two will be on the paper. And the last one here is poster 327, which is by Chao-Chin Yang, who is having a look at the streaming instability. And what they do is now they've got the largest 3D simulations of the streaming instability because they've basically increased the scale height from 0.2H to 0.8H. So they've increased the size of the box by 4 to the 4 cubed. And what they find, thankfully, is that the streaming instability is robust and they get the same results. So please go out there, have a coffee and have a look at those posters. Thank you.